measure, rewind, measure, tighter quantum random oracle model proofs for one-way to hiding and CCA security. Just a reminder, we'll have a sequence of 5 minutes of short talks and then Q&A. So if you've got questions, you can enter them in the Q&A on Zoom. Or you can either enter them as we go and we'll process them at the end of the talks, or you can save them for the end of the talks themselves. And so our first speaker is Ron Steinfeld. Go for it.
Okay, thank you. So this is a joint work with Veronika Kuchta, Amin Sakzad, and Shifeng San, and myself from Monash University in Australia, and Damien Stelle from ENS Lyon in France. So the context for this work is the Fujisaki Okamoto, or FO, transform for public key encryption. So this transform is commonly used to strengthen chosen plaintext security into chosen ciphertext security. And it's used in most of the NIST post-quantum cryptography encryption candidates. And to analyze the security of this transform against quantum attackers, we need to model the hash queries that the attacker makes, because this FO scheme makes use of hash functions. We have to model them as allow for quantum implementations of the hash function and allow quantum queries. Now, in prior work on this problem, the prior proofs for FO security only show a square root loss in the advantage of the CCA attacker. So in other words, the FO scheme CCA security advantage can be up to the square root of the advantage of the CPA security of the original scheme. And there is also a square root of Q factor related to the number of queries Q of the attacker to the oracle. So in our work, our main result is that we can remove this square root loss in the advantage. And so we get a tighter reduction where the advantage of the CCA attacks against the FO scheme is directly proportional to the advantage of the original, of the CPA security of the original scheme, up to a Q squared factor. And in fact, we can replace this Q here by D, which is the QROM query depth of the attacker rather than the total number of queries. And so it means that our new result for FO security is nearly tight for low query depth attackers that corresponds to massively parallelized attacks. So the core technical result we use to get this is a new proof for the one-way to hiding lemma. So this lemma is essentially saying that if you have two random oracles, G and H, that differ only at a single input, X star, and a distinguisher A is given access to either the oracle O, which is G, or H, and also to the encryption of X star, then any such distinguisher that can efficiently tell these two oracles apart can be converted efficiently into a one-wayness attacker against this one-way encryption scheme to recover X star. But prior proofs of this one-way to hiding lemma in the QROM again lose this square root in the advantage. And so our new result for one-way to hiding is a new proof in the QROM that avoids the square root loss. And for the one-way to hiding lemma, we only lose a multiplicative factor of D, which is again this query depth of the attacker. Now, to get this new result, we introduce a new QROM security proof technique, which bypasses an impossibility result by Jiang et al. On the previous approaches. So previous approaches to extract that secret X star were what I call query-based secret extraction, which means that the extractor, the one-wayness extractor, directly measures the distinguisher's QROM queries and tries to get the secret from that. Whereas in our new technique, which I call measurement-based secret extraction, we not only use the distinguisher's QROM queries in the extraction, we also use the attacker's quantum measurement for distinguishing these two oracles. And the way our technique works is basically we let the distinguisher perform his queries and make a distinguishing measurement, and then we rewind this distinguisher back to the query phase and make another measurement of this attacker's query at that point. So our technique involves a measure followed by a rewind followed by a measure, and that gets the name MRM. So for the future work, we hope to reduce improve further the tightness of our proof to reduce the dependence on the query depth. And we're also working on removing these two oracles used in the extractor to make it a single oracle. And we have some work in progress on the concrete implications of our results for the NIST PQC encryption candidates. And we are also investigating other applications of our MRM technique. So I'll stop here and thank you.
Great. Thank you very much. We can applaud virtually. And our next speaker will be, I'm going to mangle the pronunciation, but Yvke Dulik, and
yes.
telling us about secure multi-party quantum computation with a dishonest majority. This is a topic close to my own heart. And again, you have the floor. Can you share your screen?
Yes. All right. Yeah, so in this talk, I'm going to present a protocol that we constructed for secure multi-party quantum computation that's secure against the dishonest majority. And this is joint work with Alex Krilo, Stacy Jeffrey, Christian Mayens, and Christian Schaffner. We're all in Amsterdam at QSoft. And let's start with a little bit the setting. So what is the thing we want to achieve? What do we want to build a protocol for? Well, multi-party quantum computation, or MPQC. The setting is we have K players, and they all have their own input register that can contain a quantum state. And their input registers contain some joint quantum states, so possibly their inputs are entangled. And what they want to do is they want to jointly compute some map that I depicted as phi here on their joint registers, so that in the end, every player gets the part of the quantum state that's sitting in the part of the output state that sits in their register. And they want to do this in such a way that their own inputs or their own part of the input state remains private, and also that they have the guarantee that their outputs are correct. And that is with the caveat that it is possible for the outputs to be incorrect, but if that's the case, then some honest party will notice and they will abort the protocol. And this kind of thing that we allow, this aborting part, it is because otherwise it's not possible to achieve the following, namely that an active static adversary can corrupt up to k-1 out of the k total players. So all but one of the players can be corrupted by an adversary that can deviate from the protocol arbitrarily as long as he is efficient. And the security that we achieve in this model is computational. So there is some underlying computational assumption. And the way we construct this protocol is with a few ingredients. The first one is we use a classical multi-party computation protocol as a kind of black box inside our protocol. We call it several times, and we kind of model this as a trusted third party, this gray angel sitting here in the middle with whom the other players can communicate classically, of course, and that can perform classical computations. And the classical multi-party computation is also, I should mention, the only part in which the computational assumptions actually come in. So we need computational assumptions to construct that, but everything we build on top of this, all the quantum part, it's all information theoretically secure. And the second ingredient that we put into this is a quantum authentication code, more specifically the Clifford code. And this is where we kind of deviate from previous approaches to multi-party quantum computation. Previous approaches were mostly based on secret sharing. So the parties shared their inputs into multiple shares with each other. But using a quantum authentication code instead allows us to kind of break away from the barrier where we can only have half of the players be dishonest. So we really achieve this, like all but one players are dishonest and still have security. And the quantum authentication code allows us to do this. And of course, the players to communicate quantumly with each other. And the total number of communication rounds that we need, it scales roughly as k, which is number of players, times d, where d is the depth of the circuit measured in the number of C0 and T gates. And then there is also the log factor, or k times log n factor, where n is some security parameter. And this communication scales in this way because essentially we break the computation up into different sub-protocols, and we have one sub-protocol for every gate in the circuit that they just execute sequentially. And just to give you a little bit of a taste sort of how our scheme came to be, it is essentially a generalization of a two-party quantum computation protocol that was presented in 2012, where they also use authentication codes, and also specifically the Clifford code, to protect the data of the players. And roughly the Clifford code, or a ciphertext in Clifford code looks as you have your data psi, some zeros that are appended to it, which we call traps, and then some random Clifford C that you apply to the entire state. And then these zeros at the end, they kind of guarantee that your state is, that you can always check that your state is still in the correct form. So you can undo the Clifford and measure those traps to see that everything is still okay. And in the two-party quantum computation protocol, they also do this. So they have two players, and they each kind of apply this Clifford code on top of each other, and they each have their own zero traps that they can, during the computation, sort of privately test whether the authentication is still fine. Of course, this doesn't scale so nicely. So if we want to go to general K players or multi-players, we managed to find a way to have the players share their traps. So the encodings look again like this sort of nicer form where there's only a single set of traps and a single Clifford key. And we come up with a way for them to kind of publicly test that the zeros are still zeros. And they do this several times during the computation. So just briefly, the kind of the summary or the takeaway, we construct a protocol for multi-party computation of quantum circuits. It's actively secure against k-1 out of k dishonest players. And we kind of achieve this by generalizing a two-party computation protocol by shifting the point of view of all the players privately verifying stuff to a public verification of the authentication. But I'll stop. Thanks.
Okay, thank you very much. So again, questions we'll save for later, but if you want to start putting them in the Q&A and so we can sort of process them and queue them up, that would be great. If you could stop sharing your screen, and Christian, if you want to share yours.
Right.
Great. So the next two talks are both by Christian Mayence, one on efficient simulation of random states and random unitaries, the other on quantum access secure message authentication via blind unforgeability. And so Christian, you have 10 minutes to split between the two talks.
Okay, thanks. Yes, I would also like to use this opportunity to thank everybody who contributed to making this virtual event happen. The first talk will be about efficient simulation of random states and random unitaries, and this is joint work with Goran Alagic and Alexander Russell. So here's an overview over our results. We study the simulation of random quantum objects, so that is random quantum states and random unitary operations. And in this context, we develop a theory of stateful simulation. That's kind of a quantum analog of what's fairly trivial classically, which is called lazy sampling. So for random quantum states, we develop such a stateful simulation protocol that's efficient. And for unitaries, we can also do that, but in this case, we can't prove that it's efficient. We can only prove that it runs in polynomial space. Finally, as an application, we design a quantum money scheme that's unconditionally secure, both in terms of unforgeability and untraceability. First, to motivate the problem, let's have a look at a classical problem, which is the simulation of a random function against a distinguisher that has oracle access to it. So here we're talking about a function, say from m bits to n bits. There are several ways to simulate it. The first one is kind of the trivial way of straightforwardly sampling such a function and then using it to answer queries. This is, however, infeasible, right? This is prohibitively expensive as soon as the inputs is not too small. Therefore, there are a number of options to do it more efficiently. For example, if the distinguisher is limited to a constant number t of queries, then we can use what's called a t-wise independent function, and this can be done efficiently. Complementarily, we can also use a pseudo-random function, in which case there's no query limit, but there's a runtime limit on the distinguisher, which is polynomial in some security parameter. And finally, there's this lazy sampling, which is a very simple technique that exactly simulates a random function by just sampling the outputs on the fly. And the only price we have to pay for getting this exact and unconditional simulation of random functions is that we have to maintain a state between answering different queries. Now, in this talk, we are looking at quantum states and quantum operations. So let me quickly say, what are these? A quantum state is just a unit vector in a complex finite dimensional vector space. So it's kind of an element of the sphere, or even more precisely, of the projective space inside that complex vector space. And quantum operations are represented by unitary matrices on that same vector space. So basically, these two sets, the projective space and the compact Lie group of unitary matrices, they're both very nice mathematical objects, which have a natural notion of a uniform distribution. This distribution is called the Haar measure, and it's, of course, a continuous distribution because we're talking about continuous spaces. So we can talk about uniformly random quantum states and unitaries, but these are continuous random variables. If we now look at the same table that we looked at for the random function, but just for random quantum states, we can again look at the exact simulation that, of course, in this case, requires kind of an infinite amount of randomness, so that's completely infeasible. We could also imagine discretizing it, but that immediately implies kind of a query limit or a limit on the number of copies of this random quantum state that we can hand out, because the error builds up per copy. If we already have that limit, there's a more efficient thing to do that we can do, which is kind of the quantum analog of t-wise independent functions. And there's also a pseudo-random version. Pseudo-random quantum states were recently introduced by Ji, Liu, and Song, and later studied by Brakersky and Shmurli. What we now add to the mix is kind of the lazy sampling way of simulating. So we have an efficient but stateful simulator that unconditionally simulates a random quantum state against an unlimited distinguisher, both in the terms of number of queries and in terms of runtime. So now the picture for unitaries is very similar, except that at this point we don't know a construction for pseudo-random unitaries. But again, we can kind of contribute a stateful simulator of random unitaries that is space efficient, at least. Finally, as an application, we can construct an unconditionally secure quantum money scheme that's both unforgeable and untraceable, so it preserves the privacy of the users. And this is based on the simulation scheme for quantum states. Okay, so with this picture of a person lazy sampling, I'd like to thank you for joining today, and I'm looking forward to the questions.
All right, thanks.
Now,
And you can switch to your next talk whenever you can start whenever you're ready.
that's right. Oh, sorry. Okay. Yeah, so oh. Is it visible now?
Yes, we can see your screen.
Okay. The next talk is about quantum secure message authentication via blind unforgeability, and this is joint work with Goran Alagic, Alexander Russell, and Fang Song. So here's an overview over our results. We study the classic notion of unforgeability, but now under quantum chosen message attacks. In this setting, we propose a new security definition, which we call blind unforgeability. And this new security definition is necessary because a previous proposal by Bonnet and Jandry from 2013 has some problems that were identified even before our work. But we also have a very clear separation scheme as one of our contributions between this notion by Bonnet and Jandry and intuitive security on the other side. And as an additional result, we prove security of a number of natural schemes according to our new definition, and we relate our notion to UFCMA and to this previous notion by Bonnet and Jandry. So the threat model that we study is what's called quantum access security. This is a strong security model or a threat model where we allow an attacker quantum oracle access to a secret key functionality, like for example, the MAC function of a message authentication code. And this quantum access is modeled as shown on the slide. So why would we study such a model? There are a number of answers. First of all, such a security is possible to achieve. So why not? That's a nice thing to have. In addition, there are some applications in composable post-quantum secure in cryptography that one can imagine. And this is, for example, if we publish an obfuscated circuit of a secret key functionality, then a post-quantum threat model attacker can, obtain quantum access to the input-output functionality. And finally, there might be reasons for because of physics, but this is kind of a bit more speculative. So here is the standard security definition for MACs and digital signatures, which is called UFCMA. This is the classical notion. So it works like this: an attacker can just ask an oracle for example, for the MAC functionality, a number of tags for different messages, and finally it has to come up with a new message tag pair, M star T star, which needs to be different from all the ones obtained from the oracle, and it needs to be valid. So here, let's try that for the quantum setting. Here is an example that shows that this is maybe not so easy. So consider an attacker that prepares a uniform superposition over all messages, then queries the oracle to obtain a uniform superposition over all message tag pairs, and then measures it to obtain a random message tag pair and outputs it. This is clearly just a quantum obfuscated version of the attacker that just makes a single query and outputs the result. But on the other hand, kind of the result, the forgery is very different from the query. So in some sense, UFCMA doesn't seem to make sense anymore in the quantum setting. In addition, there are problems due to the so-called quantum no cloning principle, which prevents us from keeping a transcript of queries, and also because of measurement disturbing. So checking any condition will, in general, disturb the quantum state. So here's our new approach. And we define kind of a blinded version of, for example, a message authentication code in the following way. We take the message space and we sample a random epsilon fraction of all the messages. Now we set the blinded version of the MAC to be the plain MAC on all but the blinded set, and on the blinding set, the small fraction, we just set it to some error symbol, the bottom symbol. Now, this blind unforgeability property says that for any adversary, it is difficult to forge a message tag pair so that the message is inside the blinding set if this adversary is provided with oracle access to the blinded version of the MAC or the digital signature scheme. Turns out that this notion has a number of nice properties. For example, it's equivalent to UFCMA if we restrict to a classical oracle, a random function-based MAC, and also Lamport one-time signatures are secure under this definition. It applies the previous definition by Bonnet and Jandry, it classifies all the known examples that we have correctly, and also it's amenable to the hash and mag or hash and sign paradigm if we use an appropriate hash function. That's all I wanted to say. Thanks for being here today, and I'm looking forward to some questions.
Great, thank you again. So let's thank all the speakers. We can't really applaud, but we'll try to do that. And we've got a bunch of questions, and I guess it's a bit of a, I'm not exactly sure how best to proceed. So a number of questions have been answered on the Q&A already by authors, and that's fine, but maybe it would be good to go over a couple of the ones that had more, you know, a couple of the questions. So not sure how we should go about selecting the questions, but like maybe we'll start with questions for Ron. We'll just sort of go more or less in order of the talk. So there were two questions for Ron, and maybe Ron, you can summarize your answers for them. One of them, the ones that you were able to kind of answer conclusively. So maybe one question about decryption failure rate affecting the tightness in your result. And then how this affects, and then there were a couple of questions about how this relates to the current NIST proposals and what you currently know to say about that. Maybe you can start.
Yes, so so about the decryption failure effect on the tightness of the proof. So the slides I showed hid this part of the dependence. So there is an extra additive term in the CCA advantage, which is linear in the decryption failure probability and also in the number of queries of the attacker and the query depth. So, but that kind of term exists also in prior work as well. So that's about the decryption failure, and yeah, about the implications for the NIST proposals. So we are currently working on this topic. So I cannot, I'm not yet in a position to say a lot about it, but soon we'll be able to say more. But it looks like so far that most of the NIST candidates do satisfy the injectivity requirement that we need in our proof, so we can apply our results to them. But yeah, we'll have more to say about it in due course.
Great, thanks. Should we switch to maybe a question for Yvka? You were asked about just clarifying what quantum authentication codes are here and what role they play in the protocol.
Yeah. Sorry for not explaining this properly. It's essentially the quantum analog of a classical message authentication code, only one that then works to sign and verify quantum states. So there's like a coding procedure with which you can, like with a secret key, you can sign the state or encode the state. Then you can send it or store it or whatever, and then you can at the end decode it using a secret key as well. Or verify it, and then you can see that it hasn't been tampered with, essentially. So if the verification accepts, then you have the guarantee that with high probability, whatever comes out is the state that was authenticated in the beginning. And the role that it plays in our scheme specifically is that this way the players can kind of inject their inputs into the protocol and send it around freely and be sure that the other players don't do anything to it that they're not supposed to do. And becomes a little bit more complicated because actually they do want to do a computation. So we kind of do some key updates on this authentication code so that only certain operations are allowed. And this authentication code kind of gives a handle on that.
Yeah, thanks. And maybe to add a further point that also such authentication codes necessarily are actually authenticated encryption schemes, right? That's part of
That's just something that's not true in the classical world, but in the quantum world it is, yes.
All right, let's maybe move to some questions for Christian. And Christian, maybe I'll even let you pick. One question was about efficient simulation. To what extent efficient simulation affects Google's quantum supremacy claim? Yeah, that was about your first talk. So why don't we start with that?
Yes. So I had not thought about these two research results before. So our efficient simulation result and Google supremacy experiment. That's because they are very different in the sense that random unitaries are much more random than random circuit families for circuits that are not too deep, that are like efficiently computable. In particular, random unitaries include all unitaries, including, for example, inefficient quantum computations. So therefore, I don't think these two are related.
Great. And then there were, several questions on the second talk, on the authentication measure. And maybe I'll even let you choose which one to start with, if you have an opinion.
Yes. So I see that there are several questions about how the blinding set is sampled. So let me maybe comment on that. So we sample the blinding set by putting each message into it with independent probability epsilon. So that's, I said something that's almost that in the talk, but in more precisely, we sample it as a set of independently chosen elements from the message space. And so of course, one option that we also thought about is to give the adversary more power by letting them choose the blinding set. So we kind of opted out of that because of two reasons. So first of all, it makes things more complicated because you can't just specify a set of a very large size. So in principle, we would then need to let the adversary specify an algorithm that checks membership in that set, for example. So that kind of makes things more complicated. And on the other hand, also, we have an argument that such a notion will not be more powerful, at least, asymptotically. So giving the adversary detailed control over the blinding set will not make them more powerful, except for polynomial factors. This, I think, answers two of the questions. Maybe let me answer Andy Hülsing's other question. So that's about the implication of our notion that implies the previous security notion, whether that's tight. And so my comment on that is, with this blind unforgeability, unfortunately, nothing's tight. Like there are essentially, in some sense, not even the definition is tight, because perfectly fine forgeries are disqualified just because of the fact that they are not in this randomly chosen blinding set. That it's even hard to learn for an attacker. So somehow, if one was to extract kind of concrete security claims from that, a success probability of an adversary would need to be rescaled in some sense. And in the same way, somehow this implication is actually not tight at all. Actually, it has like a power 3 advantage loss. Are there more that I didn't answer yet? Are there?
There was one more question about how you're working.
They keep coming, yeah.
To the Zandri's work on recording quantum queries.
Right. So actually,
yeah,
we extensively use the Zandri formalism for superposition oracles as a proof technique. So both the implication of our notion implying the notion by Bonnet and Zandri, as well as, for example, the security of the Lamport signature scheme. So what I kind of didn't say is we can only prove that if we model the one-way function that the Lamport signature scheme is based on as a random oracle, then we can prove the security of the Lamport one-time signature scheme, and that's also using the Chandry superposition oracle technique.
Great, thank you. Are there, at this point, I think we've covered the questions from the audience. Panelists, are there questions you'd like to raise? I have a few.
Yes, if I may. I have a question for Ron. I want to know how do you explain rewinding after having done a measurement?
How do I explain?
How do you because if you've done the measurement, then so you mean rewind after actually having collapsed in the measurement, or some
Yes.
other version?
Yeah, after the collapse, we do a rewind back. Yeah.
I also have a question for Ifke. So you talked about the classical MPC helping to do a procedure for verification, and the verification included decrypting with a Clifford, etc. So how do you explain that the classical MPC is helping to apply a quantum operation?
So the classical MPC is never actually applying a quantum operation itself, but it kind of serves as a trusted classical memory, so to say, during the protocol. So in the beginning, the Clifford keys are stored kind of inside the classical MPC's memory. The keys are also decided by all the players sort of inputting random keys, and then the MPC multiplies them to get the actual key. And if at least one player honestly inputs some randomness, then the MPC will get a random key. The MPC will do like key updates throughout the protocol, and then at the end, he will release the relevant parts of the key to the relevant parties. And you play some other roles as well, but sort of the backbone is this essentially. So he is a classical party. He never actually does the quantum operations, but he releases the information that's relevant to certain parties at a certain point, and make sure that he never releases too much information.
Okay, thanks. I have a question for Christian about his first talk. You talked about the HAR quantum money scheme. And is this a public key quantum money scheme or private key? And then a follow-up question to that is, what is the money verification procedure, both in the HAR random one and in your case for efficient?
Right. So this is a secret key quantum money scheme. And in the HAR, like in the ideal scheme, the HAR money scheme somehow is a secret key quantum money scheme in the usual framework. And their verification is just performs like the setup is somehow sampling one single HAR random quantum state, and then copies of it are handed out as bills. And the verification is just the measurement: do I have this state or anything orthogonal? Now, in the efficient version, now the price we pay is that the bank needs to maintain a quantum state, which is then kind of the private key in some sense. So now not only the users need quantum memory, but also the bank needs quantum memory. And what ends up happening is actually, instead of handing out copies of a random quantum state, the bank maintains an entangled state with the users. And basically, verification roughly involves, using a private register of the bank and the handed-in bill register to kind of uncompute a certain amount of entanglement, and then checking whether that succeeded.
So does this mean that the bank needs to hold an individual quantum state per note that it produces, or how does the memory of the bank scale with the number of money notes that you actually that are in circulation?
Yeah, I mean it scales not so favorably. It scales linearly with the number of nodes. So it kind of actually, I mean, the memory of the bank needs to be exactly the same size as the collective memory of all the users.
And I guess this is necessary to actually get statistical type of security, or we don't know this. One would
think
guess,
one can-
maybe.
Yeah, like the point is, given that we also want like, unlimited scalability. So without a priori bound on the number of nodes we want to hand out, then I think one can prove that this is necessary.
Thank you.
Great. I have a question, maybe for Yvka. So what? So the scheme is the kind of plan for the sort of structure of the scheme that you use, which is also in some of the previous work, seems to be it's going to necessarily have round complexity that increases with the depth of the circuit that the quantum circuit you're applying, because of the fact that you're using these authentication codes and that they support only certain classes of operations and require interaction to support them. So the question is there any hope for constant round protocol for constant round multi-party computation protocols? And is there any understanding of like what might be sufficient in terms of conditions on authentication codes, for example, for that to work, assuming the classical part can be made a constant round, which is presumably an easier thing to think about?
Well, thanks. I think that really depends on whether you're interested in a constant round classical communication or a constant round quantum communication. I think in the first case, at least with our approach, it's going to be hard. Even if the classical multi-party computation is constant round, we call it several times. So then our protocol will still have multiple rounds. And our focus has been mostly in trying to minimize the amount of quantum communication, which could be like a good first step, like quantum communication between the players. And currently we need a round of communication like between all the players for every C0 gate and every T gate. We know how to reduce it so that it's only sort of twice for every T gate. So once for an entire Clifford and then once again for a T gate. But that then kind of also increases the size of the message that they have to send during that round. So there's a bit of a trade-off there. I think it might be worth kind of thinking about it a little bit more. If this can be reduced, there's not really a fundamental reason why it should not be. It's just that we can find a more efficient protocol in that sense. But I think the first step to take was to see if you can reduce the amount of quantum communication.
But in your protocol, it's not the case that you can hand all the quantum states to one party. So you're saying in your protocol as it is, there are many rounds of quantum communication?
Yes, that's right. So in our protocol, during the computation, the players need to check every now and then whether the states are still kind of in the correct state.
I see.
Again, we are not really sure if this is completely necessary, but it was necessary to sort of produce the proof. But maybe you can come up with a protocol where you reduce this amount of testing throughout the protocol. And for a test, they actually need to like send the state around a bit. So yes, there is quantum communication during the protocol.
Right. And for the two-party case, is it known? Well, okay, I'll
It's similar there, yeah. For the two-party case, they also send back and forth during the computation.
All right, perhaps we have time for one last question. And if not, we should thank the speakers again. Christian gets double thanks, and thanks again. And so we'll see you at the next session, which starts whenever Yuval says it does.
Yeah, in 15 minutes, quantum cryptanalysis, 2 p.m. UTC. So see you all, kind of a correlated crowd. So see you all in 15 minutes. Bye, and thanks everyone. It's been a great session.
Bye.
Bye.